I exit my.
Okay. Why it's not the same?
You can test, then can hear the sound.
Zoom also. Okay, so I will resume. So, like I said, there are actually four main systems of GNSS constellations, and I think the important part to know is that most modern receivers track all four. So in Singapore, I think it's very important because there are many tall buildings and viaducts that actually block the signal. So if your receiver can see, say, 25 satellites instead of 4, you actually maintain quite a high level of precision, even in very dense urban areas such as the HDB or retaining walls, for example. So a little bit more about GNSS. Actually, it's called trilateration. So trilateration is different from triangulation. Triangulation is actually something that we talk about in traversing. So trilateration is actually measuring the distance to the satellites and not the angles. So each distance is a sphere, and when the spheres intersect, that is where our GNSS readings are going to be received. So on site, basically, even if you cannot see a physical benchmark on site, you can still tie your survey points into the global coordinate grid, which was explained in 2 lectures ago. So I think I want you to imagine that if you're installing some kind of instruments on a slope where you don't have an existing control point, a GNSS will let you create these control points within centimeters, which can be verified later with the total station. So this technology has transformed how we monitor projects independently. So I think this discussion is a little bit more on GNSS within the same system and out of the system. So previously we were discussing the 4 separate systems: the European system, Russian, the American one, and in this case, if it's within the same GPS system, they actually share the same time reference, which is the GPS time and signal structure. So when they start to solve the equation on trilateration, you can get it much faster. However, if it's a trilateration across systems, for example, it is GPS and Galileo, you still form your sphere, but each system actually has a different time standard. And when you have this different time standard, you need to resolve the time differences. And that actually gives 1 or 2 more unknowns in the equations to solve. It will definitely take a longer time, but it will be slightly more accurate. So 3 segments to any GNSS. The space segments discussing the satellites, the control segments discussing the ground stations, which I will talk about it in detail, and the user segments, which is us, surveyors, engineers, and the equipment. And actually, when you start to understand the segments of the GNSS, you can troubleshoot the errors. So if it's a constellation count suddenly dropping, then it's a space segment issue. And if your corrections are lagging behind, it could be a control or user issue. So a little bit about the space segment. So the space segment consists of a minimum 24 satellites orbiting very, very high up in space. They circle Earth twice a day, repeating each ground track about 4 minutes earlier. So if you take your GNSS readings at say like 1:30 today, and if you take the same GNSS reading at 1:30 tomorrow, actually the satellite geometry is not the same. So that's why you need to check some additional values before logging in your GNSS readings. The control segment is the one that keeps your satellite data accurate. So ground stations measure their actual position and the clock drifts. They do a lot of corrections to your data and basically ensure that the readings that you receive are correct. So there's this master control station. I think it's over here. So it's actually in a Space Force base in Colorado Springs. And from there, they have 5 worldwide monitoring stations in blue. Not super important to know, but you just need to know that Hawaii covers the specific coverage. Ascension Island covers the Atlantic Ocean. Diego Garcia covers the Indian Ocean. And I don't know how to pronounce this, but the atoll in the Marshall Islands actually control that part of the world. So each of these stations continually observe the satellite signals. They measure the drift in the satellites. They measure the orbital deviations, and there's a constant correction to keep the timing and positioning accurate. So I think a bit more about the control segment. They actually right now I want you to know that this GNSS that you receive is not something that is just done in Singapore. It is actually a global framework all around the world. And when you press a button, actually you are trying to receive something that's thousands of kilometers away. And from this position of the satellites thousands of kilometers away, you're supposed to do trilateration, or rather the system will do trilateration to give you your exact point in the coordinate in centimeters away. So I think you need to appreciate the scale of this technology of signals bouncing in space and back down again. And maybe something to emphasize is that it's actually a worldwide network, and there is this infrastructure that's constantly working to keep our data accurate. Yeah, so I think this is just showing that the signal is bouncing back and forth from space and back again to us. So this last part, the user segments concerns us. I think over here it's defined as anyone that consisting a civilian or military, anyone that uses a GPS receiver. So you see in this funny example of a car that has like, I don't know, like what, 10 or 12 GPS monitors monitoring the road. On the left, you see a surveyor mapping a beach. And because it's difficult to establish control points that are half in the water and half on land, especially during some tidal conditions. So a GNSS can be very useful for that. And of course, you see like a handheld or GPS on the right. So they also help to determine your position. And I think what we want to show here is that actually there's a lot of GPS usage for civilian purpose. I think even for like Google Maps, getting around every day, I think it's something that you use on a daily basis. So for civil engineers, we actually we use GNSS to track our piling rigs positioning to prevent damages to nearby services. I wanted to let you know about a drainage job in Admiralty. Our equipment had GNSS installed onto their mast, and those were linked to the Singapore Siren RTK. So because of this linkage, the operator can georeference his location accurately in real time. And this ensures a safe distance between our work and the services. So it definitely improvement to productivity, and it's much safer for operations. So in this GPS positioning, there's 2 basic methods for determining the position, code ranging and carrier phase measurements. Generally, the code ranging is a lower accuracy compared to carrier phase. So you'll know that it's when we say low accuracy, it's within 1 to 5 meters. So something like that you can't really use for survey data. So in this slide, I think in order to achieve like a higher accuracy, we use carrier phase measurements. And actually, these measurements are much more accurate. And for engineering work, we almost always rely on carrier phase. Yeah, and that's also why in certain situations, GNSS can actually replace total stations for preliminary kind of data, and you can get pretty accurate results that you can use for your feasibility study almost instantly. So this is something like what the GNSS will look like on site. Yeah. I think most of the surface is beaming upwards towards the satellite. And basically what it's trying to do is trying to receive as many constellation satellites as possible in order to give us an accurate reading. Okay, I think this topic is important, talking about sources of errors. So even satellites make mistakes. I think GNSS errors fall into 3 big categories. So the first is satellite dependent. Second is a receiver dependent, and the third is a signal dependent. So we'll just take some time to go through some of these errors in detail. So satellite dependent errors. So just now, remember we mentioned something about uh different systems, different constellations, and different systems actually have different system times. For example, the European satellites are operating on their own European system time, and the Americans are also operating on their own different system time. So I think clock errors is something to take note. And when you start to offset the clock errors, you can result in meter level kind of errors. Orbital errors is when the satellites are moving and orbiting around the globe, they actually rely on a series of calculations to actually tell where they are. So orbital errors are when satellites are not exactly where the models say they are, and that's where you get the mistake. And I think for satellite geometry, when satellites actually start to cluster overhead, because we have, I mean, just now we were mentioning that satellites circle the Earth twice a day, and sometimes because of this, they don't circle back to the same point at the same time every single day. There are certain points of time where there are too many satellites on one side of the Earth, and there are not enough on the other side of the Earth. So there are also ways to mitigate that. Okay, receiver dependent errors. So receiver dependent errors actually, like just now there was a picture of the GNSS equipment on site. So I think receiver dependent errors, there are 2. I think the first one, clock errors. Every GNSS satellite actually carries internal clock. And in this internal clock, I think it uses a quartz kind of quartz crystal to control. So when there are errors in this seconds calculation, there's actually a clock bias, and this may add up when you continue to survey the site. So I think it's important to continue to calibrate your GNSS receiver on a yearly basis or before you attempt a big project, just to ensure that your clock bias sensitivity is kept to a minimum and you can get accurate readings on site. Second one is antenna errors. So antenna errors are when your GNSS receiver is not centered. So if it's slightly off to one side, say 1 degree to the side, and actually you get like a misplaced reading. It's very, very minor. It's quite hard to detect, but it's important that even for GNSS, you try to keep it as straight as possible, and you can reduce down these antenna errors. Yeah. So signal-dependent errors. Signal-dependent errors are errors between your satellite and your receiver. So even if your satellite is perfect and your receiver is well calibrated, it's perfect as well. The radio signal actually has to travel, say, about 20,000 kilometers. So there's all kinds of distortions that can happen as it travels. So we are starting to explore that in detail. So the first is atmospheric errors. Like we said, it's about 20,000 kilometers up. There's all kinds of different kinds of atmospheric layers. And as the radio signals bounce back and forth, their signal speed actually changes. When the signal speed changes, you actually measure it longer than what it really is. I don't know if that makes sense or not, but the denser the medium, the slower the signal, there are some difference delays, and actually these delays sort of add up. So especially if you are measuring something that is quite hilly or quite the terrain is quite steep, you measure some GNSS data at the bottom of the hill, and you slowly make your way up the terrain, up the slope, and you measure. And actually, there's this height level difference as well as atmospheric level difference. And then sometimes the delays will add up, and you need to sort of like resolve it. There's also multi-path errors. This is definitely the most common errors in Singapore. I would like you all to substitute the picture of the Grand Canyon you see on the left, right, with like more like HDB blocks or in the CBD area, and there's not a lot of, you can see the sky, but actually it is the images are shiny. It's like a glass building, and there's a chance that the signal path that the GNSS receiver takes is a reflected one, where it bounces off a surface and then go up. When that happens, actually, sometimes it's smart enough to detect a multipath error, and sometimes it's not. So when it's not, you'll get a coordinate that is very, very off your current reading. And this is actually quite common in Singapore. You will see like a zigzag pattern in your GNSS. And when you see that, actually, you need to be quite alarmed. And it's usually because of this multipath error. So some things to take note of is you need to keep a clear view of the sky. Stay about 3 to 5 meters away from any metallic structures or any shiny surfaces. Try to be aware where the signals could be reflected from. Yeah, and then if you receive a bad error or a bad reading, you can do it again and you can do a correction after that. So the third error is cycle slip. The cycle slip is basically you have like a poor quality connection with a ground station, and you lose the connection. When you lose this connection, actually, you're unable to verify some of your data. For example, your multipath errors, or is it like an atmospheric error and stuff like that? Yes, there's a little chance for automatic correction. So I think for us, when we do GNSS surveys along PIE, there's a lot of traffic going through the expressway. And when we start to survey the drainage on the side of the expressway, actually we start to see that our invert levels are jumping, maybe up to like 150 millimeters sometimes. So we need to be quite mindful of these errors. We suspect it's from the passing buses and the passing trailers that bounce these reflected signals off. But with some GNSS processing on site, you can find the errors and then you can go back to the same point to take it again. So I think the only mitigation is that you got to spot it early, and it's got to make sense to understand why are the sources of errors, so that you can be quite mindful when you're on site and you can spot them before bringing it back to the office, because it'll be too late by then. So I think this slide is like a summary on signal dependent errors. They also talk about a little bit about atmospheric delay, and they talk about multi-path errors. So I think this slide is pretty useful to understand the sources of errors. And I think in Singapore, especially in the construction sites, you have steel, you have water, you have high humidity. Understanding these sources of errors differentiate like a professional surveyor from somebody that just goes there to push the GNSS button. So I think the GNSS accuracy is not just what is in the sky, but also what is around you on the ground, and do your readings that you take actually make sense or not. Okay, so a little bit more about surveying methods with GNSS. So there are three main methods that we'll go through: static, rapid static, and RTK. So each one has its users, so we'll try to go through that shortly. So in static surveying, we use this to fix the position of control points. And you need a high level accuracy. I think similarly, you can see the picture on the right. There's a yellow color tripod. We center it, we put the receiver there, we extend the mast, we collect data for a long time to ensure that we have as many constellations as possible. And the more important part is actually we want the accuracy to be about 5 mm horizontally and 10 mm vertically. So we need it to be as accurate as possible. We do not move the GNSS, and we put it on a tripod to minimize most of the sources of errors that we were discussing earlier. So once you establish this control point, it's just as good as transferring it with a total station, and you already have a temporary benchmark from where you can chart out the rest of your levels on site. So rapid static surveying is like the same as static, but like faster. So instead of like a few hours per point, maybe we do it like 10 or 15 minutes. Uh, I think we would have already done the static surveying, and then we just want to quickly establish like a terrain map or contour line of the slope, and we use this technique to say chart out a slope contour to understand roughly where the points are every 10 meters or so, and you can get your data quickly without sacrificing too much accuracy. Okay, so this is introduction to RTK surveying. So RTK actually stands for real-time kinematic surveying, and this is what we use on site most frequently. We can get the results in real time. There's actually some kind of SIM card involved. We can also check the measurements and verify them on site. So it's quite good for setting out, and you can get it at like a centimeter level accuracy. So there is a lot of corrections that we are seeing as we are moving the RTK receiver on site. We transfer from a known point, and we set up with a GNSS. So with the known point, I think just now we talked about ground stations. We have a live correction, and you can as you move around the site, the GNSS receiver will continually correct it together with the base, with the ground station. So I think for like setting up a drain, the RTK means you can stand at where the sump is, and if you're a little bit off, say you're 20 millimeters off to the left, you can do another correction backwards. You adjust again, you lock in the correct point, and then you move on. So I think this kind of application is very good for accuracy. And the good part is that you get the results back in real time. So you can double check information before moving on to the next point. So in Singapore, we use this thing called a network RTK as well. So a network RTK is I think operated by SLA. SLA has this siren. I think I went through it a little bit, but this is on like a UK version of it. Yeah. So your GNSS rover connects to the mobile network, and I think I mentioned like a SIM card just now, and basically it connects to the 4G grid, it bounces back to the ground station, and then back to your receiver again. So this way of communication, the real-time one, is really useful on site, and it can help to reduce a lot of errors. Okay, so I think back on errors again, they do not remove any site-dependent errors. So you still got to look out for tall buildings or reflective surfaces that might cause some of these multipath errors. What RTK actually does overcome is your satellite kind of errors. Yeah, your clock errors, your satellite errors, and this one they definitely help to overcome. But you still got to be quite mindful of where you take your readings on site. And if you have, you find like a weird reading, you should actually go back and do it again. So the line of sight to the sky still matters. If you're under a bridge, you're under a tree, you need to either get out of it, or you got to switch to some other methods like a total station. And I think it's important to always verify any random points that you see. And you can definitely do it easily with a total station because you already have like a known point. And I think the most important part is the technology can only help you, but you need to know how to use the technology. So you still need to be aware of the sources of errors and then use the technology wisely. So for the SLA siren network, these are some of the ground stations that we connect to, and the ground stations help to reduce down the accuracy to, like you can see here, like 10 millimeters in the horizontal, and verticals of 20 millimeters. Okay, so I'm actually done with the GNSS section. I think the next couple of slides, the next 4 slides, I wanted to touch briefly on one or two technologies that is I would say an enhancement to the GNSS. So I think one of it is called the 3D laser scanning, and it's getting more and more popular. So a 3D laser scanner actually sends out like thousands of laser pulses every second, and it measures how long it takes to bounce back. So from that, you will hear things like point clouds, you will hear things like XYZ kind of coordinates, and they actually capture a lot of the details of the surfaces around the laser scanning device. So you can see even like a tree root image can be captured in high resolution, similar to like a picture, and that is only possible with a 3D laser scanner. So in order to get this kind of high resolution image, if you were to use it with something like a total station, you will take like a super long time. Like maybe like in a day we can do like 200 points with a total station. But something like a laser scanner, you actually capture millions of points in a couple of minutes. And this kind of level of accuracy can be really, really useful when you're taking the data back to the office to digest. I think at Hocklim Engineering, we actually use 3D scanners to capture existing drainage channels before we start our work. The 3D scanner actually produces a very detailed 3D model showing things like cracks and drainage outlets and alignment of the walls, which is far beyond what manual measurements will be able to show. So, for example, in one of our previous work along Orchard Road, we did a 3D scanning of the Stamford Canal underneath Orchard Road, which is near like Hilton Hotel all the way to Ion Orchard. So we scan the canal walls underneath to understand the structure and to do some as-built survey in order to plan some of the other activities that will be carried out on top of this drain slab. And the point cloud was exceptionally useful to recreate like a 3D model where we do capacity checks and we do beam modeling calculations for the PSPC beam that we found. And it really helps to get a lot of information with a short amount of time. So I think with technology, some of these things that previously would take like months to do could be completed in weeks. And basically with a 3D laser scanner model, if you combine it with like a GNSS control point, then your scan becomes fixed onto a grid. And that can really help you make sense of this information. I think another technology is LiDAR. LiDAR is short for light detection and ranging. So I think it's very similar. It's also laser light, and it's also many points. And with that, you can capture 3D models. You can capture 3D uh, maps of objects. I think the iPhone also has like a LiDAR scanner. So you can use that to I don't know, build like 3D models or something. So I think most importantly, different levels of LiDAR scans have different levels of accuracy. So I think similar to what we say, it's also a laser kind of device. And if you sweep the laser in all directions, you have quite a very dense 3D point cloud. And from that, you can use to do some kind of manipulation. I think for civil engineering, we actually use LiDAR in 2 or 3 ways. I think we have like an aerial LiDAR where we go onto the drone and we try to map uh, things like reservoirs or terrains that are quite inaccessible. And of course, we also have like mobile LiDAR where we sort of mount it onto a vehicle and then we drive it through a city and then we try to scan things. So I think what is good about LiDAR compared to other kinds of technology is that it can actually see through vegetation and like a ground cover. So if you need to sort of scan the slope that is heavily vegetated, or you want to scan through a forest, this kind of technology is useful to remove the trees and the vegetation on the surface so that you can properly analyze, say, like a slope contour and remove the effect of vegetation on your survey, which is you're not able to do with traditional methods. So I think this is an example of an aerial kind of LiDAR. And with that GNSS 3D mapping, and of course LiDAR scanning. They actually form the foundation of digital surveying today. And hopefully this lecture is quite useful for you. I will hand it over to my colleague Pei Cao that will go through the next section on setting up.
Okay. Stop recording first.